In the next example, this is actually a really cool problem because it does a number of things. What we're going to do is we're going to evaluate the volume that's bound by a paraboloid. The paraboloid's given as z equals x squared plus y squared, but we're not evaluating the entire volume. Essentially what we're doing is we're making a little slither inside of the xy plane, and it's bound by these two functions, 2x and x squared. And the first thing we're going to do is we're going to evaluate it as a type 1 region. I always suggest to students to graph the area in the 2D plane first, because that's going to help you to govern and to develop your region. Alright, so in a 2D plane, I'm just going to draw that out really quickly, and then I'm going to show you what it looks like in the 3D plane as well, as best as I can. Now we know y equals x squared is just a parabola, concave up. Alright, so this is our function g of x. So that's g of x. And then our function f of x, it's going to be our line, our linear function, which looks like this. I know mine's not linear, sorry, much more difficult to do. Okay, so that's our function f. Now, what we're looking for is this region in here. Okay, so this is the region that we're binding. And clearly we can see that g is the lower function, f is the upper function. And what we'd like to be able to do is we'd like to also be able to identify the limits of integration by identifying the points to which the two functions intersect. Alright, so that's fairly easy. All you do is you just set the two functions equal to one another. Most of you can just see this by inspection that it's going to be 0 and 2, but let's verify it algebraically. So we're going to set f equal to g, which implies 2x is equal to x squared. I'm going to subtract x squared from both sides. I'm going to factor in x. And clearly, we can see that the two values from x are going to be 0 and 2. All right. So, what we can see is that y is going to range from the bottom function, which is x squared, to the top function, which is going to be 2x. And that's just in our 2D plane. Then we can see that x is going to range from 0 to 2. And this is our domain D. Alright, so that might be the first thing that you always try to do, is to evaluate the domain D. And you can do that by constructing the graph and then doing a little bit of algebra by setting the functions equal to one another. Let me try my best to give you an idea of what we're actually finding in the 3D plane. Alright, so we're not finding the entire volume, so we know what an elliptical paraboloid looks like. Alright, so I'm going to do my best here in 3 dimensions. So here's our 3D plane. Okay, let's just assume this is x plus, this is y plus, and this is z plus. Alright, just for construct. And then we have our elliptic paraboloid that looks something like this. Alright. Now, remember, we're looking for the region that's going to be bounded by a parabola as well as a line. Alright, so if you just give me a second, I'll try to do my best here and draw it in another color. Alright, so we have our parabola, and then we have our linear function. And just imagine in this paraboloid that if I was to try to do something like this, to where we have this sort of thing going on, all right? And then we have the volume that's cut out inside of this elliptic paraboloid, all right? So essentially what we have, just think about this. We have this, and then we have this area. So those are the areas that are kind of binding this, and then we have it inside of here. Okay, so I can't really give you a really good image of this, but just think of it that that's the volume that's going to be inside of what you have there. Alright, so that's what this double integral really represents. Alright, so now that we know what it represents, now remember, there's two different ways to evaluate this, and we're going to evaluate it first as a type 1 region. Remember, type 1 regions go up and down. So I'm just going to go ahead off to the side and again graph it, just so you guys can see what's going on with this. Okay, small graph. Here's our parabola, here's our line. And remember, type 1 region, if you can draw up and down and it only intersects inside of the area at one point, then it's going to be a type 1 region. Now remember our double integral. Remember, rules of double integrals say that you're going to take care of the variables first. Okay, so we're going to go back up. We see that x squared and 2x are the bounds. And then remember, we found 0 to 2 are the bounds on the x. The function, x squared plus y squared in 3 dimensions. And then the order of integration, remember y ranged from x squared to 2x, so it should be dy and then dx. Right. So at this point, what I would recommend is try to go back and just pause the video before we complete the evaluation, and then rewind it, look through this again so you can get a good idea of how to set it up. In particular, this region that I graphed and the region that we constructed D. Those are the most important parts of being able to move forward. So now we're going to evaluate. An evaluation should be fairly easy at this point. We're going to integrate with respect to y. So now we have integral 0 to 2. The antiderivative of x squared with respect to y is going to be x squared y. The antiderivative of y squared, add 1, divide by the new exponent. So 1/3 y cubed. Y is going to range from x squared to 2x, and then we still have that dx going on in here. So here's our dx. All right. We're not worried about dx yet. In fact, once we get to dx, we're pretty much done. We're going to substitute the upper and the lower bounds. All right, and this is where it's going to get a little bit tricky. All right, not too bad though. Integral 0 to 2. Upper bound is 2x. So we're going to get, I'm going to put a bracket here. We're going to get x squared times 2x plus 1/3 times 2x cubed minus, now we're going to substitute the x squared back in. So that's going to be x squared times x squared plus 1/3 times x squared cubed. All right, so that's our integrand now. Now we still have dx. We certainly don't want to evaluate this without doing a little bit of simplification, or in this case, a lot of simplification. All right, so 0 to 2, still our bounds. X squared times 2x is going to be 2x cubed. We have 2 cubed, which is going to give us 8/3 x cubed. We have a negative sign, so that's going to be minus x to the 4th from x squared squared. So notice we have a minus sign, x squared squared. Minus is going to carry over. X squared cubed is going to be x to the 6th. Remember, you multiply. So 1/3 x to the 6th. Right. We still have a sneaky dx in there. I just ran out of room. So we have dx there. Now clearly we can combine the like terms at the beginning. Right. That's going to turn into 14/3 x cubed. So we have 0 to 2, 14/3. Right, because 2 and 8/3, 2 is 6/3, 6 and 8 is 14. So we have 14/3 x cubed minus x to the 4th minus 1/3 x to the 6th dx. And now it really just turns into a Calc 1 problem at this point. Right? So again, if you're having trouble, pause the video at this point, go back and see where you might have made an error or where you were lost. All right. I'm going to continue to finish this by using fundamental theorem of calculus one last time. We're going to evaluate the antiderivatives. Okay, so we're going to get 14/3. Antiderivative of x cubed is going to be x to the 4th over 4 minus x to the 5th over 5 minus 1/3 x to the 7th over 7. from 0 to 2. So we're going to simplify, then we're going to substitute, then we're going to compute. Okay. If you could verify, 14 and 4 are going to cancel. This turns into, I believe, we're going to get 7 over 6 x to the 4th minus 1/5 x to the 5th minus 1 over 21 x to the 7th. Again, from 0 to 2. The good news is this time, because it's a polynomial, the lower bound is inconsequential because it's 0. All right, so we get 7/6 times 2 to the 4th minus 1/5 times 2 to the 5th minus 1 over 21 times 2 to the 7th minus 0. Okay, we really don't care about the 0. All right, and then finally what we're going to do is we're going to compute. Give me one moment and I will do that. And my answer is 216 over 35. If you could check that to make sure that that looks good. If it doesn't look good, then I'm going to have to redo all 12 minutes of this video again. Alright, so again, go back through the video, make sure that you understand what the volume is, also understand how to graph the area in the XY plane, graph the volume, understand what the domain D is, and then understand how to get the limits of integration. The fun part comes in the next part where we evaluate this as a type 2 region.